Okay, so what if I told you there's this hidden language, a kind of secret code that's running pretty much our entire digital world? And no, I'm not talking about Python or C++. This is something deeper, a language of pure structure and transformation. Today, we're going to start deciphering that code. We're talking about linear algebra.
Yep, it's linear algebra. And believe me, it is everywhere. It's behind the 3D graphics in the video games you play, the algorithms that recommend your next favorite song, even the massive models that predict the weather. But to really get a grip on how it shapes our world, we've got to start with the basics. It's really a new way of thinking, a powerful new language that, once you learn to speak it, brings a ton of clarity to complex problems. All right, let's jump right in. And to learn this new language, we are not going to start with some dense, dusty textbook. Nope. We're going to start with a puzzle that I'm willing to bet you've seen before. Ringing any bells? A classic system of linear equations from school, right? The goal is to figure out the one specific value for x, y, and z that makes all three of these statements true at the same time. And if you remember trying to solve this by hand, substituting one into the other, it can get really messy really fast. But what if there was a better way, a more elegant, more organized way to see this whole puzzle? What if we could just translate it into the language of linear algebra? Well, we can. All three of those tangled equations can be compressed into this one beautifully simple statement. A times x equals b. It has the exact same information, just written in a new, much more powerful shorthand. So, what exactly are A, X, and B? Let's break down the grammar of this new language. First up, the matrix. Now, don't let the name throw you. A matrix is literally just a grid of numbers. That's it. It's like a spreadsheet, a way to keep things organized. We describe its size by its rows and columns. Think of it as just a container for our numbers. And a vector? Well, a vector is just a special, much simpler kind of matrix. It's a matrix that only has one single column. So it's just a tall, skinny list of numbers. In our cool little equation, ax equals b, both the x and the b are going to be vectors. And this is where it all clicks. This is how the translation works. The big matrix A is just all the coefficients, the numbers in front of the variables, plucked out and arranged in a grid. The vector x holds our unknowns, our x, y, and z. And the vector b holds the constants, the numbers on the other side of the equal sign. See, it's the exact same puzzle, just in a new, much cleaner language. Okay, so now that our puzzle is all neatly packaged up, how do we actually solve it? Well, this new language comes with its own toolkit, a super simple, systematic way to find the answer. Believe it or not, these are the only three moves we need. They're called elementary row operations, and this whole process is sometimes called Gaussian elimination. You can swap rows around, you can scale a row up or down, or you can add one row to another. That's it. Those are the complete rules of the game. And here's the magic. By just applying these three simple rules over and over again, you can systematically untangle that matrix until the solution for x, y, and z literally just pops out. It takes what felt like a messy, creative problem and turns it into a reliable step-by-step recipe. But honestly, solving one puzzle is just the very beginning. The real power of this language isn't just about finding a single number. It's about understanding a much deeper, much more fundamental idea, the idea of transformation. So I want you to start thinking of a matrix, like our matrix A, not as a static box of numbers, but as a machine. It's a function, a map, that takes in a vector, does something to it, and spits out a new vector. This is exactly how graphics engines move objects around a screen. But it can't just do anything it wants. To be linear, this machine has to play by the rules. It has to preserve the structure of the space it's working on. And this slide shows that difference perfectly. Look on the left. A linear transformation is well behaved. Grid lines stay parallel, they stay evenly spaced. If you transform two things and then add them, it's the same as adding them first and then transforming the result. The structure is totally preserved. But now look at the right. A nonlinear transformation just breaks everything. It warps and twists the space. The sum of the transformed parts isn't the same as the transformation of the sum. That's the real key to being linear. It never ever breaks the underlying grid of space. So, if all these matrices describe these predictable, structure-preserving transformations, is there some kind of fundamental law that governs them all? Like a law of conservation for these operations? You bet there is. This is it, the rank nullity theorem.
It looks so simple, but it is a profoundly important truth about how transformations work. You can really think of it as a conservation law for dimensions.
So let's decode that real quick. N is easy. That's just the number of dimensions you start with. In our puzzle, we had an X, Y, and Z, so we started in 3D. Rank is the number of dimensions you have left in the output. For instance, a transformation could take a 3D cube and flatten it onto a 2D piece of paper. The rank would be 2. And nullity is the dimension of whatever got lost, the number of dimensions that got completely squashed down to 0. In that flattening example, we lost 1 dimension, so the nullity is 1. And that is the fundamental law. The dimensions always have to add up. For our flattening example, our starting dimension, n, was 3. The output dimension, our rank, was 2. The lost dimension, our nullity, was 1. And what's 2 plus 1? It's 3. The books always balance. A transformation can stretch, and it can shrink, and it can rotate space, but it can't just create or destroy a dimension out of thin air. So, there you have it. We've translated a puzzle, we've uncovered the rules of transformation, and we've revealed a fundamental law of conservation. We've just learned the basic grammar of this incredibly powerful hidden language. So the real question is, now that you can see the matrix, what other secrets of our world do you think you can unlock?